So can you see these slides? Well, good afternoon to all, and welcome to this live session of Energy Conversion Technologies. So in this live session, first of all, I will brief you about the assignment examples, which are almost, I guess, all of you must have answered during assignments. So I'm just quickly run through the assignment solution as well as the answer, and you find it whether you have ticked a proper answer, or whether you have answered these questions correctly. So if you see the week 2 assignment in that, because I am not going through these theory questions, so mostly the questions which are related to the numericals that I am just trying to highlight, just make you comfortable while solving this example in the exam as well. So that is the main purpose, to highlight these assignment questions along with this solution and then the answers, so that if you have any mistake while solving these examples, you can just rectify these assignments questions, or as well as you can say the when answering in the exam, the final exam, I would say. So if you see here the week 2 assignment, there was one example about the common data, which was asked to calculate the high reading value of carbon. In that, basically the example was related to analysis of a particular fuel, that is a biomass, which was given, and in that it was asked to calculate first the high reading value of the given biomass sample. Third is basically the to determine the maximum annual amount of the CO2 emissions from the plant before flue gas desulfurization. And the first was like basically just to find out the general formula for the given biomass sample. So if you remember, we have solved this kind of example in the regular practice sessions as well. And in this case, the ultimate analysis is given as carbon, nitrogen, sulfur, and oxygen in the respective amount. And this biomass is consumed in a power plant at a rate of 10 ton per day. And the plant uses the limestone flue gas desulfurization unit. So this we discussed elaborately during our discussion in the one of the lecture with 90%, and this is with the 98% efficiency. So the HHP of the carbon, sulfur, and hydrogen, it is given here. So with the help of this, now we have to first of all determine the general formula, which is in the form of CHXOY, because here C is considered as 1 mole, so that's why we have not represented in the form of CX. Okay, so X and Y we need to estimate here first of all. And this is very simple way to estimate it, because if you remember this H by C ratio formula, that is percentage weight of H by its molecular weight divided by percentage weight of carbon divided by its molecular weight. So once we, because these values are already known from this particular data here, right? So once we use this value, we get the H by C ratio as 1.5. Okay, and then similar way we can find out the O by C ratio, where it tells you the amount of H and O, right? So it's O by C, that's why it is O by C and the H by C ratio. And here C is 1 mole, right? So accordingly, based on that, the value of H is 1.5 and O is 0.7. So once we represent this formula in this manner, it comes out to be in the form of C, H 1.5 and O 0.7. And similarly, quickly we can estimate this HHV for the given biomass sample. As we know, it's a mass fraction of carbon into its high reading value, then hydrogen into its high reading value, and sulfur into its high reading value. And this is because mainly this carbon, hydrogen, and sulfur in the solid fuel are oxidized into CO2, H2O, and SO2. And that's the reason the reading value has been calculated with respect to these elements, that is carbon, hydrogen, and the sulfur. And their heading values are already given in the example. If you see, these are the heading value for the respective element here. Once you substitute this, it comes out to around 24.27, and that was the answer. And similarly, the maximum annual amount of the CO2 emission from the plant before flue gas desulfurization. And we discussed this topic in very elaborate way in one of the lecture. And also we solved one example on this, if you remember, So it is very simple because the annual consumption of sulfur in the coal is given in the example itself, right? It is 0.2, okay, and then per 100 kg of the biomass, and 1 ton we have to calculate on a per 10 ton per day basis. So once you convert that into a specific, right, quantities, and then per day basis, because that was if you see here the conversion, so based on that we can convert it into a per day basis 365, and then it comes out to be around 7300 kilogram of sulfur. And then the complete combustion of this sulfur, it is as you know, this is the reaction. So 1 kilomole of sulfur, it reacts with to produce 1 kilomole of the sulfur dioxide, and we know 32 kilogram of sulfur burns to produce around 64, because 32 plus 32 it is 64, right? And then this is the amount of sulfur which is burned, and so it produces around 14,600 kilogram of sulfur dioxide. That is the answer, that is 292 and 14,600. So similar way, these particular examples were actually solved in the practice session as well, if you I think if you remember correctly. So that particular example, if you can try to solve in a multiple way, that time also I told, then you can have the different aspects of this kind of examples. Similarly, the week 3 here, in this case, it was mostly based on the charcoal, right? And how to calculate the ash content on dry basis. So here also the common data is given, and based on that there were 3 particular examples were asked to calculate specific quantities like ash content at dry basis, then energy yield of carbonization process, and then calculate the mass yield on as received basis, dry basis, and the dry ash free basis. So these are very simple example with a simple formula we have to make use of. Proximate analysis is given, and the ultimate analysis is also given here. And in fact, the experimental studies also show that 40% of the waste is converted into the polarities, which is carrying 20% of the total thermal energy. So this also information is given. And if you remember this simple formula, ash on dry basis, it is ash by 1 minus m. Clear? So now with the help of this, you can just simply replace the moisture content here. Ash content is given as 20%, that is 0.2. So it comes out to be around ash on dry basis is 21.74. So that was the answer actually for this question. Similarly, the energy yield of carbonization process. So as you know, it is stated that 40% of the waste is converted into the volatiles and carrying 20% of the total thermal energy. So 20% of the total thermal energy is going basically, or you can say it is getting lost with these volatiles. So that is 1 minus 0.2. It is simple. So 80% is the energy yield. So and the last in this case was to calculate the mass yield on as received basis, dry basis, and the dry ash free basis respectively. And these are basically the simple equations which are used to calculate these values here, because the remaining and the rest of the information is given in the example. And mass actually we can say the mass yield on as received basis is equal to total feedstock minus mass lost into volatile. So that is 0.4 into 100 gram, because we are considering it only always on the 100 gram basis, right? Considering the 100 gram of MSW. So that is 40. So 100 minus 40 is equal to 60 gram, that is 60%. So similarly, once you know mass yield on as received basis, moisture content is known, remaining things we can easily calculate. And ash actually as is given in the example, similarly once we know these two terms here, then you can easily calculate the mass yield on the dry ash free basis, and that comes up to around 55.56. So like this example, the answer to this example is 60%, 65.2% and 55.6%. So likewise, these things are actually calculated very elaborately in this way here. And then now once we go to the next example, which is a week 4, where we need to calculate the respective amounts of the hydrogen and the carbon monoxide which is required to produce 100 kg of ethanol using Fischer-Tropsch synthesis process. And if you remember the reaction for the Fischer-Tropsch synthesis, which is the generalized reaction, which is shown here in this form. Here. So now once we do balance of this particular, once you try to balance this reaction, then it requires 2 moles of CO2, 4 moles of hydrogen to produce C2H5OH and H2O, that is ethanol. So if you remember this formula in the one of the lecture, we discussed about this, how to calculate the respective amount or the weight of the particular hydrogen carbon monoxide in the Fischer-Tropsch synthesis process. So this is the basic formula which we have used there. That is the weight of ethanol into N, that is nothing but moles of hydrogen into molecular weight of hydrogen, divided by moles of ethanol into molecular weight of the ethanol. And once we know this weight of ethanol, it is 100 because it is given here 100 kg of the ethanol. So it comes out to be around 17.4 kg. And similarly, carbon monoxide, it comes out to be around 121.7 kilogram of carbon monoxide. So this is also one of the easy example which was given in the assignment to solve. I hope you must have, all of you must have answered this easy example as well. I guess there are no much difficulties in this kind of examples. These are very simple examples and very straightforward as well. This is another one where we need to calculate the amount of heat which is required to raise the temperature of the feedstock from initial temperature of 30 to 500 degree Celsius. That is basically a simple example where we need to know the, you can say, specific heat, first of all, right? The specific heat of the sample is need to be known. And then the it was municipal solid waste, so the value was given. So based on that, if you just calculate the MCP with the help of formula of Q is equal to MCP delta T. So M is given here, CP is also known, and then delta T is 470 because 500 minus 30 is 470. And once you simply multiply this, it comes out to be around this many megajoules per day. So this is the right answer to this question as well. And the next is the to estimate the agricultural waste requirement of a given pyrolysis process. So this is also very simple example here, because if you see these examples, these are very simple in nature, in the sense is like we need to know only the specific formulas which are required here, and with the help of that formula we can easily calculate the specific given information. So in this case, the agricultural waste has a calorific value of 15 megajoule per kg, and the furnace has overall efficiency of 75%. So with the help of this, we have to just calculate the agricultural waste which is required, and it is just heat required divided by calorific value into its efficiency. It comes out to be around 1 ton per day. It is very simple calculation again. And here actually we need to determine the residence time of the feedstock inside the reactor. The volume of the reactor was actually 8 kL, that is 8 meter cube, and the municipal waste has a density of around 250 kg per meter cube. So with the help of residence time, that is reactor volume by the volumetric flow rate, we can calculate the residence time. And once we know the residence time is equal to reactor volume divided by mass flow rate by its density, that is nothing but the volumetric flow rate. And these values we already estimated, which was given, and then it comes out to be 1.6, 1 by 6 day, that is 4 hours. So another simple example to practice this kind of calculation. And in the example, which is week 5, a biogas plant producing around 1 meter cube of biogas on daily basis, which produces around this much amount of the LPG with the amount of the LPG here per month. LHV of the biogas is given, as well as the LPG of LHV is also given. So biogas produces around 1 meter cube per day. And as you know, the low rating value of the biogas is this much. And once you multiply it, it comes out to be around 22 megajoule per day. So this is nothing but the amount of the, you can say the energy, right, per day basis. And then you can convert it into per month basis also if you require. And the LPG, the LHV value is given as 45 megajoule per kg. So once you divide these two, once we'll come to So here we can get the value in the form of 14.7 kg per month. So that means this much kg per month of the LPG can be replaced by 1 meter cube of biogas plant. So another very simple example. And if you remember, this kind of examples we already solved in the practice session as well. Another in the similar line is on average a daily cattle produces around, this is basically a manure which is around 30 kg on total wet manure per day basis, which is having moisture content of 80%. Density is this much. Biogas yield of around 0.26 meter cube per kg of dry manure. So with the help of this, we need to calculate the volume of biogas digester, which is suitable for the output of 100 dairy cattle, right? And assumption here is retention time of 21 days. So this is the right answer for to this particular example here. And its solution is very simple because we need to know only this volume of the digester formulas, and we can calculate the mass flow rate of the dry manure which is required to input into the digester. Once we know these values, we can easily calculate the volume of the biogas digester required. So 30 kg per day per cattle, and once we know the moisture content is 0.8, so 1 minus 0.8 equal to 0.2 into this 30, right? It comes out to around 6 kg per day per cattle, that is the dry manure produced. And the mass flow rate of the dry manure input into the digester is 6 kg per day into the 100 cows, so equal to 600 kg per day. And the volume of the digester, because here QF into TR need to be known, and QF we know is the volume flow rate of the digester fluid, and it can be calculated from the mass flow rate, right? How? Because this is QF is equal to M naught by rho M. Isn't it? So this is the density of the, here if you see the density of the manure. So 600 by this density, it comes out to around 12 meter cube per day, and the retention time is known, that is 21. So once you simply multiply these two quantities, 12 into 21, it comes out to be around 252 meter cube per day. So this is the answer to the simple question. Similarly, there was an example which was also on the common data, where the common data was also given in the assignment to calculate basically the theoretical ethanol yield from the fermentation of fructose. So here in this case, 1 ton per day of the fructose was fermented to produce the ethanol, and the ethanol is used as a fuel in the internal combustion engine for power generation. The thermal efficiency of the engine at the maximum power is 40%, and the heat of combustion of the ethanol is known, that is 26.9 megajoule per kg. And once we know the hexose as a sugar which is we use for, that is nothing but the fructose is used for the fermentation. So we know this simple equation here, which use 2 moles of ethanol, 2 moles of the CO2. And here it is given that 1 ton per day of the fructose, that is 1000 kg sugar per ton of the biomass. Clear? And into 0.51 is the theoretical ethanol yield per kg of sugar. So it comes out to around 510 kilogram of ethanol per ton of biomass, right? So that is 510 kilogram per day. That is on the daily basis, because this is the input which is on the daily basis. And another thing to calculate in this example is like the CO2. And once we know the 0.49 is nothing but the CO2, actually it's a typo here, it should be CO2 per gram of sugar. So it comes out to around 490 kilogram of CO2 per ton of biomass. So that is nothing but this much kilogram of CO2 per day will be produced during the fermentation of 1 ton per day of fructose. So this is another simple calculation in the assignment. And now with the help of this, we need to calculate the power which is generated by the use of ethanol in the system. So ethanol production rate is known, 510 kilogram per day. Its calorie value is known, 26.9, and the engine efficiency is 0.4. So once we know these terms, we just simply multiply these terms, and we get the value in the form of 63.5 kilowatt, because here we need to do small unit conversion here, because the answer, it may comes out in the form of first megajoule per day, and then with the help of unit conversion, you can simply convert it into a kilowatt. That is kilojoule per second. So joule per second is a watt. kilojoule per second is a kilowatt. So accordingly, you can just simply convert the unit and get the final answer, which is 63.5. In assignment 7, because if you remember the assignment 7, it was mostly on the combustion and the gasification and the pyrolysis, about the process of the combustion, gasification, and the pyrolysis, where we need to calculate the concentration of the nitrogen gas, which is in the flue gas. If 1 mole of the coal presented by the formula, which is given here, is completely combusted using the stoichiometric amount of the air. So now once the coal is given as a feed material, we know coal contains some amount of the oxygen in its composition. So accordingly, we need to select a specific stoichiometric equation. And if you remember, we discussed this stoichiometric equation as well in one of the lecture. And once we know this equation here, so the 1 mole of the CO2, moles of CO2 produced in this particular product is here A equal to 1 mole. Moles of H2O in the product is B by 2, that is equal to 0.8 here by 2, that is 0.4, and moles of nitrogen in the product is equal to 3.76 into A plus B by 4 minus C by 2. Once you substitute these values here, so we get the C here nothing but 0.4. Okay, so this one, because this C we are trying to get it from this equation here, HCA HBOC. So C here is 0.4, and once we know these values, just try to substitute these values in this equation here, and we'll find out we'll get the value of mole fraction of the nitrogen, that is 72.87, that is round up to 72.9. So sometimes you may find this kind of small round off error in the calculation. So say for example here the answer comes out to be around 72.87, whereas in the answers which I mentioned here it is 72.9. So you have to round off your answer to nearest digit, right? Okay. Similarly, with the help of this example, we can calculate the dry exhaust, because this is the coal which is burned under the overall mean condition, and the measurement of the dry exhaust give mole percent of this much. So with the help of this, we have to calculate the excess air percent. So percentage excess air formula is simple formula. Here, as we know, CaHbOc. So this is B, this is B, and A is 1. Once you simply multiply, replace these values here, and the mole fraction of the CO2 is 0.1 and the oxygen is 0.08. So it comes out to be around 72.72. This is the answer. And it was asked to calculate the equivalence ratio. So equivalence ratio calculation, we can make use of this simple formula, because once you know the percentage excess here, then we can simply calculate the equivalence ratio using this equation, which comes out to around 0.58. And the equivalence ratio, that is lambda, it is, as we know, it is inverse of the equivalence ratio, that is 5. So it comes out to around 1.73. So likewise, these simple examples were given in the assignment to solve, and even you can practice this kind of examples. So I hope you all must have answered these assignment questions properly, and if not, I think this today's live session would help you to understand these, can say, the solutions. With the help of these solutions, it would be really helpful to you to solve these examples, as well as now the examples on the similar line will be asked in the final exam. So you can practice the example in the similar line as well. Okay, so try to practice the example in the similar line. So if there is anyone who has any query, so we can simply try to discuss those queries first of all. So is there anyone who has any query regarding the lectures, or we can say some component in any of the lecture?
Hello, sir. Good evening, sir.
Yes.
Yes, sir. I have few questions related to this biomass energy. Can I ask?
Yeah.
Yeah, sir. Can you just brief about any bioenergy policies? The energy, what is the kilowatt hour? How much is it the same as well as the non-renewable energy which is producing? The energy production policies related to those informations. Can you put some light on that, sir?
No, I did not
And
get your question.
also the and also how this how biomass energy conversion technologies like about what is the principle used in that one. Suppose if I have some 5 tons of biomass in my own farm, if I want to convert that, what are the things I need? And like as an entrepreneur, how I can able to do this myself? Like I just want to have some more information related to that one. If you want to sell the biomass energy to the uh, grid, means what is the procedure I need to follow? Such kind of information would be helpful for me.
Yeah, actually, because these are mostly related to the policy matter. So, as you have mentioned, your first question is related to the policy matter. So, there are actually the basic guidelines are already given about the biomass policy because biomass actually is a vast, basically the fuel. You can convert it into different kind of energy source. So once you go by the anaerobic digestion, the things are slightly different. Once you go for the ethanol fermentation, the things are different. When you go for the biomass gasification, then again the things are slightly different. So it is based actually which particular process you want to adopt. So the policies based on that, actually already some of the guideline and the policies are already available. The portals, respective portals, I would say. There are certain schemes related to the anaerobic digestion process as well. So what kind of help can be provided to the entrepreneur if they want to go for the some kind of plant, installation of some plant. So example, if you have the specific biomass available, so if you remember the our lecture in module number, I guess, 2, where we initiated our discussion on the biomass, there we explain the kind of characteristics which we need to take into consideration before finalizing the specific process for the biomass based on the moisture content. Suppose the moisture content is too high, so which kind of process can be adopted? If the moisture content is too low but the high reading value is in the low range, so which kind of process can be adopted? So based on that, because it's not directly a biomass, any kind of biomass can be fed into the particular process. Say for example, anaerobic digestion process, if you try to put, okay, it's a good wet biomass is there, but it contains a relatively good amount of the you can say the inhibitory agents. So even if you try to put those kind of material, say in the form of pesticides or maybe some kind of like insecticide, if it is too much present in the particular biomass, so those will have impact on the downstream processing of the particular process, that is during the later stage. So those specific characteristics need to be known beforehand so that we can use a specific process as per the characteristics of the biomass. And mainly, as I mentioned earlier, if the moisture content is too less, so the thermal conversion process are the best one because it gives a very good efficiency in terms of the conversion efficiency of the material. And although the temperature requirement is relatively high, but then it gives a good efficiency, process efficiency in that sense. And the another aspect is like the produced fuel can be converted into a secondary fuel as well. The second is particularly, you can say, the primary to the secondary. The secondary fuel can be converted in the specific form, liquid or gas if you require. So that is the advantage of these thermochemical conversion processes. So on that aspect, if you are having any biomass, so I would suggest you to think about the pelletization technique first of all, if it is widely being accepted in that particular locality. So that is one of the best process to go for because it also helps in the CO2 circulation. If you see, you if you have gone through one of the lecture like what is CO2 neutrality. So based on that, so that particular pellets can be used in the co-firing with the charcoal or you can say coal in the specific application. So that is also one of the good, you can say the initiative in utilization of the biomass rather than just throwing it into the as a waste. because if you see the decomposition of the biomass as such in the environment, anyway is going to again release the through the decomposition process. It will increase the decomposition period. However, it will lose most of the compound from the biomass. So rather than, you can trap those and use it as a fuel for the application purpose. If the very you can say with minimal approach and minimal processing, this is the best alternative.
Yeah, thank you, sir. Sir, right now, what is the biomass capacity in India, sir? Can you put some light in every, like in South India, how much megawatt they are producing, and in North side, how much? So, what the now what the sectors are planning to forecast how much they are going to project in the next 5 years? Those datas.
Oh, that information, in detail information about this each sector, like as you are asking, biomass or solar or wind.
No, only biomass, sir. I'm asking.
So actually, as if you recollect our discussion, as I mentioned, actually the biomass, the exact figure of the biomass, which is we are highlighted in one of the lecture, that is basically which you have obtained from the different reports. But most of the energy production from the biomass is taken place locally. As a result, it is not accountable, and hence the exact amount of the biomass utilization for the energy generation in terms of, as I mentioned earlier as well, for the production of like a co-firing purpose, or maybe for the anaerobic digestion purpose, or maybe for the ethanol fermentation purpose. So because the biomass has a wide range of the categories, in the sense is like the even the waste oil which is getting produced is nothing but sourced from the biomass material as well. So those discrete informations are available, but in totality, actually is very difficult to answer right now at this moment, because I'm not sure about the exact total amount which is getting produced, which I have mentioned in one of the lecture, but that is just available from the reports. But the unaccountable amount is still very high, because which is getting utilized locally. So as a result, that is the only information we have right now. Because similarly about the biomass, as I mentioned, it is comes sometime in the collective way, that is renewable. In that, the biomass contribution is, if you see here, is like 1% or 1.2%. But collectively, the renewable is like close to around, like say around 6% or 7%. So that way, it is calculated. But detail just in depth about this specific source, that need to be worked out actually.
Okay, sir. Thank you for the information.
So is there any query or any question?
Sir, is the biogas is in are they marketing the biogas for domestic fuel purpose as of now, or it is only utilized for power generation, sir? Is there any idea about that?
Domestic marketing in the sense is like right now, for example, those who are
So
having,
like LPG, are they packing and selling for the consumers? Is it in practice now, or it is going to implement that stage? Just want to know, like
Actually,
Adani and all
because this
gas.
bottling of this biogas, as you are mentioning about the bottling basically, bottling of the biogas, right?
Yes, sir. Yes, sir. Like
Yeah.
LPG, how
How
Indian
we
and all
do,
those agencies are
yeah,
doing.
Indian and all those they are doing. So for the LPG, the they are doing the bottling, no doubt. But the bottling of the LPG, they are doing it for the after purification, and then those particular bottle gas they are basically using as a fuel right now. But for domestic application, actually, I think the idea is like to inject this along with the in the pipeline gas, so that it will not be transported like a kind of a bottles. It will be flow through the pipelines along with the our LPGs. So that is the actually idea behind this biogas installation and the for the big installation of the biogas plants. And the bottle, basically the bottle bag, because if you see the production is uh, the way you are anticipating, it is not that high that it is getting bottled and it getting utilized. So where the locality is utilizing this kind of biogas plants, so they are directly utilizing it for the cooking purpose, either for the cooking or for the electricity purpose. So those examples are there, but then bottled and then again used it for the you can say for cooking, transporting and then cooking. That is almost very like negligible, I would say. But the online utilization is more rather than just bottling and all, because it is very, I would say, cost costly affair. So most of the time, what is happening is like the small pockets of the biogas plants are being installed, and these are directly connected to the cooking needs of the specific families or the group of families, and rather than most of, and then other gases are the rest of the gases getting utilized for the electricity generation. So in the same locality. So like these kind of examples are there. But bottling of the bagasse is almost is very well known because it is being used as a fuel.
Yeah. Thank you, sir. Sir, is it possible? Actually, biogas can be mixed with LPG and will give more efficiency. Is there such?
That's what I'm saying. The things are under progress in that particular line, where actually the mixing is trying to be anticipated like in this way, so that what percentage can be flown with this. Because as I mentioned, this is the way like it will be easiest way that produced, stored, and then injected. Similarly to say the hydrogen, so in the similar line. Although about the
Okay,
hydrogen,
sir. Okay. Yeah, please, sir. Please.
no, that's what I was mentioning. Similar to the hydrogen, like now the things are moving towards the hydrogen economy, or you can say the hydrogen as a fuel. So these kind of alternatives are being explored, like whether hydrogen can be flown along with these uh, other gases as well in certain proportions. So that way, these kind of alternatives can be explored for these produce biogas from the biogas plants.
Thank you, sir. Thank you.
So anyway, if there are no more questions, so can we wind up this live session now? Okay. Okay, so thank you all for joining the live session, and hope those who will be appearing for the exam, I wish them a very best, because the exam paper would be on the similar line as I mentioned earlier as well, and the most of the assignment examples also I have discussed during this live session. So wish you all best for the coming exam of this particular course, that is energy conversion and technologies. And thank you for joining for this live session.